Welcome. Thank you. Welcome to the Mike Lazaridis Theatre of Ideas here at Perimeter Institute for Theoretical Physics in Waterloo, Ontario, Canada. And welcome to this, Perimeter's public lecture series presented by BMO Financial Group. My name is Greg Dick. I'm the Director of Educational Outreach here at Perimeter, and it is a pleasure to welcome everyone here this evening, both those of you here in the theater and also those of you watching online on either Perimeter's website or one of our many science communication colleagues' websites around the globe. Now, tonight's lecture will last approximately 1 hour and will be followed by some question and answer. Dr. Kelly Foyle and a team of researchers are behind their keyboards ready to engage in conversation for the online audience. If you want to participate in that, use hashtag #PILive. And also, if you have a question for the presenter at the end of her presentation, use hashtag #PILive as well. And ask the question early so it has time to get to my phone. And now, it is my pleasure to introduce tonight's very special guest speaker. We are honored to have with us this evening Dr. Eugenia Cheng. Dr. Cheng is a mathematician and a pianist. She is using both of those passions in her current role as scientist in residence at the School of the Art Institute of Chicago. She has also won tenure in pure mathematics at the University of Sheffield in the UK and is an honorary fellow at the University of Sheffield and an honorary visiting fellow at City University in London. Alongside her research in category theory and her undergrad teaching, her aim is to rid the world of math phobia. In her pursuit of this, she was an early pioneer of math videos on YouTube, and her videos have been viewed millions of times. In fact, I just learned of one today that went truly viral and was over 8 million views, and it involves a bagel. So I have to wait for that. Dr. Cheng recently received her first commission for mathematical artwork and is designing chalkboard installations for the new science-themed hotel EMC2, or in this building, EMC squared, in Chicago, commemorating Emmy Noether and symmetry. As a concert pianist, she runs Liederstube, a not-for-profit organization in Chicago bringing classical music to wider and wider audiences. And tonight, she combines her love of music and mathematics to bring abstract mathematical concepts to life with her talk, How to Bake Pie. Ladies and gentlemen, Dr. Eugenia Cheng. Welcome.
Thank you. Thank you very much. Thank you. And first of all, I would like to thank the Perimeter Institute for inviting me here to give this talk. And thank you all for coming here and filling this absolutely beautiful lecture hall. And hello to everyone who's watching online. I am going to talk about math and food, as portrayed in my recent book, How to Bake Pie. And I'm enjoying the fact that for today, this is a triple pun, because not only are we baking pie and pie, perhaps we're also baking the Perimeter Institute. I love math, and I love food. And unfortunately, many people seem to love food more than they love math. And so I've decided to try and bring my love of math to everyone via a love of food. Because I've decided that math is quite a lot like cooking, actually, that really you just get some basic ingredients and do something with them, and then you make something that may or may not be delicious. And the thing about cooking is I think that it became the most fun for me when I got to just go into the kitchen and make things up for myself, and then all I had to do was decide if I thought it was delicious. And the worst that would happen is maybe I would poison myself. It's not the same as maybe being in cooking class where you're getting graded and maybe it will go wrong and that'll be terrible. Wouldn't it be sad if we had to pass tests in cooking before we were allowed to cook in our own kitchens, or even before we were allowed to go to eat in restaurants? Unfortunately, math is a bit like that, because we're forced to pass all sorts of hurdles, jump through all sorts of hoops, and pass all sorts of tests on the way up through high school math before we get to do what I think is the really fun stuff, where you make it up for yourself. And when I started doing research, I realized that I had found my home, that when you get to make up math for yourself, all you do is make up some rules, follow them using logic and see what happens. The worst that happens is that you make a contradiction and then your world implodes. But just like with poisoning yourself, you recover and you move on to another world. I sympathize with anyone who found math in school maybe not the most interesting subject. Because I didn't find it very interesting in school. I found the classes rather boring. And although there are some wonderful math teachers out there, and I had a few, also, when you're being forced to pass tests, very few of the tests are particularly interesting. And that's not the fault of the teachers. Fortunately for me, I have a mother who is mathematical, and she showed me some of the most fun and interesting pieces of math just at home when I was very small. And so I somehow held out a hope that there was something more beautiful at the end if I managed to pass all those tests, which I did, and lucky for me, I didn't find it that difficult. So I can sympathize with people who do find those tests difficult because, of course, then they'll decide to go and do something else. And I know that most people don't have a family member at home who just casually shows them fun math at home. And so I've decided to be that person for everybody, where through my books and my YouTube videos, I show some of the things I find the most fun, interesting, and fascinating. Not because they're useful, because math is useful, but I don't think that's very motivating, especially not for young people. When did young people ever get motivated to do something because it was useful? It'd be like saying, oh, I'd like you to meet my friend. They're very useful. But in fact, I'm going to show you some of my favorite mathematical structures. And often there are things that mathematicians study out of sheer curiosity and fascination. And if we study and understand those things, then often the applications and the usefulness follows later. Sometimes years later, sometimes thousands of years later. And so if we stopped pursuing these questions out of curiosity because we couldn't think of a use, then there would be so many things, pieces of progress that would not have happened for our society. So I try to emphasize the fascination and the fun of it. Just like people play music not because it's particularly useful, but because it's fun and enjoyable. And the same goes for playing sport and eating food. I rarely eat food for nutritional reasons. Mostly I eat it because it's tasty and I'm a glutton. And the same is true for mathematics. I'm kind of a glutton for mathematics. And I hope to show that everybody can be a glutton for mathematics, even if you can't do it. So I'm not saying that I can turn everybody into a PhD researcher in mathematics. But I think that everyone can appreciate what math is for, just like you can appreciate food even if you don't know how to make it. And you can appreciate music even if you can't play. And you can appreciate art even if you can't make it. I think that everyone can appreciate what mathematics is about even if you can't do it. So I'm going to show you some of those things this evening, including Bach, juggling, hair, factors of 30, cake, and custard. Now, you might not think that any of these things has anything to do with math whatsoever, but math is everywhere. Whether you know it's there or not, it's still there. And you don't need to know it's there often in order to use the thing. But I think that if you know it's there and understand it, you can use that thing better. You can maybe improve that thing. You can fix it if it goes wrong. Sometimes people say to me, yeah, well, I can get by perfectly well in my life without math. And I say, maybe, but I get on better. So first of all, to show you what is the math inside all of these things, I need to tell you what math is really. Because it's not just about numbers and equations, and it's not just about getting things right and wrong. It's about much more than that. I think that math is the study of how things work. But not any old things. It's the study of how logical things work. And it's not any old study of how logical things work. It's the logical study of how logical things work. The trouble with that is that nothing actually does behave logically. I don't behave logically. No offense, I'm sure you don't behave logically. This computer definitely doesn't behave logically. So, since nothing behaves logically, we have to do something. We have to forget some of the pesky details that prevent things from behaving logically so that they become idealized versions of themselves. And that move is a move of abstraction, where we move from the real world of objects to the abstract world of ideas. And the beautiful thing about the abstract world of ideas is that things do behave logically. Now, it's a move that can be scary. And I think this is one of the times that people get math phobia, because you do that abstract move and you don't have your feet on the ground anymore. And you don't have anything you can touch or see or play with. People often say to me, I was fine with math until those numbers became letters. And that is a move of abstraction. But actually, numbers are already an abstraction. And most of us have understood numbers such a long time ago that we've forgotten that that was an issue. But I love helping small children with math. And if you've ever helped small children learn how to count, you can see them struggling to make the move from the objects that are in front of them to these funny words that you're saying. And when they finally make that connection, then they leap on, and then all sorts of things become possible. And so you say to them, well, look, here's one banana and another banana, that makes two bananas. And here's one monkey and another monkey, and that makes two monkeys. And here's one apple and another apple, and that makes two apples. Something's going on. It didn't really matter that those were bananas or apples or monkeys. It was one thing and another thing, which makes two things. So you might as well forget all of those details and go, it's 1 add 1 equals 2. And that's a process of abstraction. And the powerful thing, well, there are many powerful things about this, and the whole course I teach to my art students at the School of the Art Institute of Chicago is called The Elegance of Abstraction. And all I do throughout it is convince them that abstraction has a purpose and is satisfying and indeed elegant. One of the things that happens when you forget pesky details about things, well, I love forgetting details about things, but lots of different situations become the same when you forget some details. Just like a lot of houses are actually the same underneath, they've just been decorated differently. And if you strip away the paint and the windows and the carpet and stuff, then you can see the structure that's holding it up. And making connections between different things is one of the most powerful aspects of mathematics. What it does is it finds what is in common with different situations, and it says, why don't we study that thing once instead of studying it many times separately? And mathematicians are fundamentally lazy. Math comes up because we don't want to do the same thing over and over again. So we make a theory that does it for us once and for all, and then we put the details back in afterwards. So I'm going to show you one of my favorite abstract structures, which is from a piece of Bach. Bach is one of my favorite composers, and it has a lot of math in it. And I could talk about the math in Bach for probably 3 weeks without stopping. So I won't do that. This piece is from the second book of Preludes and Fugues that Bach wrote. There's tons of math even just in those Preludes and Fugues, but he wrote them, it's called the Well-Tempered Clavier, because it became possible, with the help of some math, to tune instruments in every key so that every key became equally nice. Previously, you had to make some keys sound nice and some other keys sounded dreadful. But then it became possible to make them all sound equally nice. So Bach wrote a prelude and fugue in every key. There are 12 keys on the piano. He wrote major and minor, so that makes 24. And then he got really excited and did it all again. So that makes 48. And this one is from the second book, and it's in G minor, and I will play it for you now. I have to be careful sitting down. I probably shouldn't break the fourth wall, but all the microphone packs are on my thigh. So if you see me sitting slightly oddly, it's because of that. Try not to knock them off. Okay, that's fine. Thank you. Thank you very much. Now, when I first studied this piece of music, I was very confused by it. It's written in polyphony, like a lot of Bach is, which means that there are separate lines of music that wind their way around each other, sort of independently, so that you could get 4 people to sing it. So the top line of music starts like this. And what you usually do when you're studying a piece of polyphony is you start by taking each line separately and studying it by itself to see how it goes. Now, when I tried to do this with this piece of music, I got really confused about where each line was. So I decided to draw a picture of it. And the picture came out like this. This is a very extreme abstraction of the piece of music, where I have forgotten almost every detail except where each line of music is in relation to the other ones at any given moment. So once I'd drawn this picture, I could understand why I couldn't understand it. And that's always the first step to understanding something, right? Because this black line here starts as a soprano but ends up as the tenor. And the bass creeps up and ends up as the alto. And the alto ends up as the bass. And the tenor ends up as the soprano. Which means it would be a bit difficult to get 4 people to sing it. I do know one person who can sing soprano, alto, tenor, and bass, but that's only one. So the point is that once I had understood this, I realized why I was confused by the piece, because the lines of music cross over and don't come back. And usually in polyphony, they cross over temporarily, but then they come back. So once I had seen this abstract structure, I felt that I could play the piece better, even though you don't need to know that the abstract structure is there to listen to the piece. You don't have to see the picture to enjoy the piece of music. It's just like we don't have to know where the structural walls in this building are to use the building. It's just a good thing that someone knows where the structural walls are. Now, the amazing thing about this is I did this before I started my PhD in category theory. And when I started my PhD, diagrams like this came up in one of the first research papers that I read by Joyal and Street, as it happens, on braided monoidal categories. And it's amazing because there are some symmetric monoidal categories defined on this chalkboard right behind me. And these are the sorts of diagrams that come up in that field. And I did not know that this was going to happen when I drew this picture. But these are things called braids that mathematicians study to see just how the crossings work, how they float around each other, and we're going to see how this relates to juggling. Now, I used to say, I'm terrible at juggling. And then someone came up to me after a talk and said, you know, that's like people saying they're terrible at math. And I went, oh. But I really am terrible at juggling. And I went home and I thought, well, I'm really bad at throwing and I'm really bad at catching, so I must be bad at juggling. But bearing in mind this embarrassing fact that it is like saying you're just bad at math, I tried it at home and discovered I could just spontaneously juggle. I was just able to do it. And it was very strange, and I can't explain it, except that isn't it amazing how our own psychology and beliefs about our abilities affects our actual abilities? That was the lesson I learned from that. Anyway, I still don't think I'm quite good enough to demonstrate in front of an audience. So I'm wondering if there's someone here who would do a juggling demonstration for me. I have some juggling balls with me. Yes, thank you. Are you wonderful? Can you come down? Hooray! Hi, what's your name?
I'm Alim.
Alim, wonderful. Here are some juggling balls. Go into the middle so that they can see you. Don't laugh. He's doing great. Hooray! Thank you. Would anyone else? Thank you. Would anyone else like to try? Anyone else? Anyone else? Oh, you can? Woo! What's your name? William.
Fair warning, I'm a little out of practice.
Woo! Amazing. Now, do you think you could do that while walking across the stage?
Give it a shot.
Now, just before we ask William to do that again, now imagine that there's a long exposure camera taking a photo as William walks across the stage, so that each juggling ball is going to become a line. And see if you can imagine what picture that will take as he walks across the stage. Amazing. Thank you very much. Thank you. Can you see what picture it will make? Here is one that I made using illuminated juggling balls. It was not me who did the juggling. I tried, and it made a very wonky picture, so we found an 8-year-old boy in the school. Here's one that I made digitally so that you can see a bit more clearly. So what happens is that you start with, say, the green and the red balls in your right hand, and now it's going to be a comedy slow-motion juggling demonstration. The green ball goes across like this, and as it's going, the blue ball goes across like that. And then as that one's going, the red ball goes across like this, and as that one's going, the green one goes across like that. And this makes a braid, because braids come from balls or particles. So this is relevant for particle physicists as well. Particles, as they move through the air, they trace out a path. And if I turn it this way, you can see it's the same as the braid in my hair. And the thing about the braid in my hair is that we all know that you only need one band to hold a braid in your hair together. I tried to braid my hair according to this Bach braid. It didn't go very well. Because you can see you would kind of need a band floating around doing nothing really, and so is this black one. The blue and the red ones are looped up with each other. But that didn't work at all. So mathematicians study how looped up a braid is according to whether you would be able to move a strand around to make a different braid. And the fact that you only need one band to hold this in, so if I pull it out and then I pretend I'm in a hair commercial, a shampoo commercial. I always wanted to be in a shampoo commercial when I was young. There, the whole thing comes out with only one band, and that is how mathematicians study braids. And this is done as part of a field of topology, which is about shape things. And I think it was just very fascinating, but it turns out that there are applications that were not necessarily expected. Maybe for example, for advanced diagnosis of Alzheimer's disease, which is thought to be something to do with brain cells being tangled up in the wrong way by a mutation. So you need a way of being able to tell whether a tangle is really the wrong tangle or the same one, just looked at from a different angle. And you can't just stick your finger into someone's brain and take out a brain cell and wave it around to see if the tangle is different. So you need an abstract way to do it, which is related to these braids. Now, since I couldn't braid my hair like this, I decided to make a pie instead. This is my Bach pie. It's banana and chocolate. So now we're going to talk about something that is more obviously mathematical, the factors of 30. So maybe we can remember what the factors of 30 are. They are 1, 2, 3, 5, 6, 10, 15, and 30. Very good. Not very interesting. It's a bunch of numbers in a straight line. That's not my idea of fun. In fact, unfortunately, we live in a three-dimensional world. So we write on two-dimensional pieces of paper in one-dimensional straight lines. And so we always end up forcing our math into one dimension by mistake. And this means that we often destroy some natural geometry that it would have had if we hadn't been forcing it into a straight line. This is also why I don't tidy my desk, because my papers have natural geometry where they are. So let's find some natural geometry of these factors of 30 by looking at the relationships between them. And my field, category theory, is all about looking at relationships between things rather than just looking at the intrinsic characteristics of things. And what it says is that you can understand a lot about objects just by seeing how they're related to other things. Just like you can understand a lot about people by looking at how they relate to other people. And it would be quite odd to write a biography of someone without talking about all their relationships, just trying to write a sheer character study of the person. Instead, we usually talk about their family and their relationships and their children and their friends and things. So let's do this with the factors of 30. We're going to make a kind of family tree where we show which factors are also factors of each other. So 30 is like the great-grandparent at the top. And then we'll have 6, 10, and 15 that go straight into 30 with nothing in between. And then 5 goes into 10 and 15. And I don't bother drawing something all the way from 30 to 5 because that's 2 generations. Just like in a family tree, we only draw the gaps from 1 generation. So now 2 goes into 6 and 10, 3 goes into 6 and 15, and 1 goes into 2, 3, and 5. So now we see it's the vertices of a cube. And it's a cube a different way up from the way we usually think of a cube because it's standing on one corner. And this also shows something about that little brain teaser that says if you hang a cube from one corner and you suspend it in water exactly halfway, what shape does it make on the surface of the water? A hexagon, exactly. And you can see this here because the halfway point is here, and it will have to go through 3 faces at the front and 3 faces at the back, so that makes 6 faces for a hexagon. We can also see an interesting rotation symmetry. If you imagine rotating this cube, the 2, 3, and 5 will change places with each other, which shows us that they really play the same role inside the number 30. They are the prime factors. And these 3 change places with each other, and they are all the ones that are composite numbers with 2 prime factors inside them. Anyway, this is a cube, which I think is a lot more interesting than a bunch of numbers in a straight line. And we can relate this back to braids, as it happens, which is like this. We imagine that we're wrapping up a present with ribbon. And I'm going to make up some rules for my ribbon because it's math. I'm allowed to make up any rules I want. And so my rule is that the ribbon coming in from the right is going to go on top. So I'm going to follow the faces of this cube down the sides with those red and the blue. I now need a third color to come around here, so that's going to be green. And on this other half of the cube, I'm going to start the ribbons in the same places with the same colors. So red is going to start here, and blue here, and green here. And because the faces are in a slightly different configuration, I follow the faces and make a different braid. Now, if you look at these 2 braids, I hope you can see that if I shuffle this red and blue crossing down and bring this green one up, it will turn into this braid. So mathematically, these count as the same braid. And this is actually something that has a very fancy name in math. It's called the third Reidemeister move. Mathematicians love giving things complicated names because it makes us feel clever. And it's all about feeling clever, right? Except that I don't think that it's fair to keep people out of the things that you know. I think that if you know something, it's really important to share it. And I think that some people, unfortunately, derive some of their self-esteem from knowing things that other people can't understand. I prefer to derive my self-esteem from helping other people understand things rather than keeping them out. So this is called the third Reidemeister move, and it's because there are 3 moves that enable us to turn any braid into another one that's the same. Reidemeister boiled it down to 3, and then it's like a game. There are 3 moves you're allowed. Can you use these 3 moves to turn this braid into this other braid? So the first move is just where you have a loop like that and you pull it straight. The second move, you have 2 strands crossed over like that and you pull them straight, and this is the third most interesting move. The cube structure behind it is something that comes from higher dimensional algebra, which is another thing I met when I was first studying for my PhD. And that also has a fancy name called the Yang-Baxter equation. And I'm sure there are many people at the Perimeter Institute who study both of those things or use them in their work. Anyway, the point is it's about wrapping presents up. And later on, I thought, well, wait a minute, why don't I do this to the Bach braid? Because here what I've done is I've taken a present and I've wrapped it up with ribbon. But how about I take the ribbon and try to reverse engineer a present that's the exactly right shape to be wrapped up by this ribbon? So I stared at it and I thought, well, you know what? So you need a square face here for this crossing and a square face here for this crossing. It's a cube. And I looked at this and I did exactly what I do when I prove a math theorem. I went, oh my goodness, that's amazing! And then 2 seconds later I went, it's probably wrong. And then 2 seconds after that I went, probably everyone in the world knows this apart from me. And then 2 seconds after that, I went, maybe it's trivial. So, like a good mathematician, I checked to see if it's trivial. I thought maybe every braid makes a cube, which is not true because you need 6 faces for a cube, which means you have to at least have a braid with 6 crossings. So then I thought maybe every 6 crossing braid makes a cube. That's also not true because you could just take 2 strands and go cross, 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 cross. That wouldn't be a cube. So I don't know what's going on here. I phoned a friend, in fact, my friend who can sing soprano, alto, tenor, and bass, And I said, oh my God, this is cube. And he said, I think it's because Bach was communing with the spirit of the Platonic solids. And I don't think that's what it is. I don't know what's going on, and I don't know if it's useful. But do you know what? It's so cool. I don't think it matters if it's useful or not. I just think it's cool. And sometimes that's enough of a reason to study a mathematical structure. So moving on to cake. Cake is also very cool. And I like making dessert. My favorite things to make are dessert because they have no nutritional purpose. They just exist to make me happy, which I think is great. And Battenberg cake is one of my favorite kinds of cake. It's a very British cake. Allegedly, it has something to do with the crest of the Battenbergs. But anyway, you have two colors of cake. And the point is, you do not want the same color of cake to touch the same color. Terrible. So this is also a mathematical structure. For example, we can do a multiplication table for 1 and negative 1. So here we're going to put 1 times 1, which is 1 usually. Here we're going to put 1 times negative 1, which is negative 1, and here as well. And here we're going to put negative 1 times negative 1, which is 1. So it's a Battenberg cake. We can try this again using addition of even and odd numbers. So here we're going to put what you get if you add an even number to an even number, which is even. Here, what if you add an even number to an odd number? Odd. And if you add an odd number to an odd number? Even. It's a Battenberg cake. Now, not all things are Battenberg cakes. You can do multiplication of even and odd numbers, and that won't be a Battenberg cake. And you're not my student, so I won't try and trick you, but I do give it to my students, and they all merrily fill it in as if it were a Battenberg cake. It's not. However, this one is real and imaginary numbers. Now, imaginary numbers, you may or may not know or ever have known what an imaginary number is, but it's that thing that happens when they say to you at school, you can't take the square root of a negative number. And then the following year, they go, okay, now we're going to take the square root of a negative number. So imaginary numbers are what you get when you take the square root of a negative number. Do they exist? Well, does anything exist? They don't cause a logical contradiction, and therefore in mathematics we can play with them. As soon as you've thought of an idea in math, you can play with it. And I love that about the abstract world. It's not like the world of Lego, where my nephew has to bug my sister for the Batman Lego set. Oh, please, I think it's the Ninjago one. That's the one he likes the most now. Please, can I have the Ninjago Lego set? Please, please. No, as soon as you've thought of a mathematical idea, you have it and you can play with it. I wish that my dinner would also work like that. I could just think of my dinner and it would exist. So let's try this out. Even if you don't understand how this works, it's a Battenberg cake. So real number times a real number is real. A real number times an imaginary number is imaginary. And an imaginary number times an imaginary number is real. So it's a Battenberg cake. There's a slight zero issue, but we'll ignore that for now. So related to this is bed flipping, and this is why I've given you all a little piece of paper with A, B, C, and D on it, because in case you hadn't noticed, it's a bed, or rather, it's a mattress. And the point of mattress flipping is that we're supposed to flip our mattress every season to stop our kind of fat bottom from weighing into one part of the mattress all year. I never do it because I'm much too lazy. But if you were going to do it, surely you would write A, B, C, and D on your mattress to remember where it's been before, right? So this is one of the problems with real-life math questions. Usually they're so contrived that nobody will be fooled about how useful they are. My favorite one is one that my friend Sally told me about. My friends love sending me their children's homework to see how ridiculous it is. And this one went something like this. You have 1 meter of string. You use 35 centimeters of it to tie up Joe. You use 30% of it to tie up Eddie. How much do you have left to tie up Sally? And besides the fact of why are we tying people up, 35 centimeters is not really very long to tie someone up with. Anyway, this particular problem is quite nice, so I'll forgive it the fact that its real-life application is not very applicable to me. We can make a little multiplication table for the different ways we can flip our mattress. So here is 0 and then 0, which means you never do anything because you're me. So you always stay in the A position. Now, rotation, I'm calling rotation this way. So this is where you do nothing and you rotate, you get into the B position. This flip I'm calling flipping over sideways. So you get into the C position. And then flop is flopping over that way, flop. Very difficult to flop your mattress over. And besides which, these days, if you have one of those foam tops on your mattress, you don't want to flip it over anyway. But anyway, it's D. So going down here, you do the move first and you do nothing afterwards, which should produce the same result, because it doesn't really matter when you do nothing. You can do it anytime you want. I like doing nothing. So you get the same answers coming down the side. So now here, let's try doing a rotation and then another rotation. So we do a rotation and then another rotation. You get back to A. And here we're going to do a flip and then another flip. So we do a flip and then another flip. Also A. And here we're going to do a flop and then another flop, which is also A. And what that tells us is that if we keep doing the same move, we'll just keep getting back to the beginning again and we will never hit the other positions. So we need to try and combine things a little bit. So let's try doing a rotation and then a flip. So we rotate and then flip over sideways, D. And then here, we rotate and then flop. So we rotate and then flop, C. Here we do a flip and then rotate. So we flip and then rotate, D. And then here, start again in the A position. This is the entire point. I get to say flip, flop. So you go flip, flop, B. And then maybe you can start guessing from the pattern. What do you think is going to go here? C. And what do you think is going to go here? B. Good. And now, because we're good mathematicians, not people on the internet, we could check that this is actually true by testing it out. I'll tell you it is true, because the main question now is, how many Battenberg cakes are there? So there's 2 here. There's 2 more here. There's 1 in the middle. But there's my favorite one, which is the big one, because the whole cake is a Battenberg cake, each of whose small cakes was already a Battenberg cake. So here's one I made. I put the letters on it so you can show which one is which. I call it the iterated Battenberg cake, because we've iterated the process of Battenbergification. And mathematicians are really like small children who, once they've done something once, they just want to keep doing it over and over again. And I think it's because of conservation of energy. If we can do it once and just repeat it, why don't we do that? So Battenbergification is like painting by numbers, where all I have to tell you is what goes in position 1 and what goes in position 2. So it could be yellow and pink, it could be chocolate and more chocolate, it could be a bunny and another kind of bunny. I've now Battenbergified a bunny. Or it could be one kind of Battenberg cake and another kind of Battenberg cake to make the iterated Battenberg cake. By the way, if you try and make an iterated Battenberg cake, you have to cut off so much cake to make everything fit together that you end up with basically more leftover cake than cake. And then you make lots of friends. Now, here is a very extreme abstraction of the Battenberg cake, because all I'm telling you is what goes in position 1 and what goes in position 2. Once I've told you we're doing Battenbergification, this is enough information. And abstraction is sometimes like finding the most efficient way of representing information. So this could be yellow and pink, it could be light brown and dark brown, it could be bunny 1 and bunny 2, it could be cake 1 and cake 2. But what is cake 1? Cake 1 is already one of these, and cake 2 is already one of those. So why don't I take this picture for cake 1 and put it where it says 1? And I can take this picture for cake 2 and put it where it says 2. This is now a very extreme abstraction of the iterated Battenberg cake, where all I've told you is which things are going in, and then because we know each of these points is a point of Battenbergification, this makes the Battenberg cake. This is something that mathematicians study. It's called a tree, because it kind of looks a bit like a tree, where the tree starts here with the roots and then it branches up like this. Mathematicians get into very strange arguments about which way up their trees should go. Some people really think they should go the other way up because obviously trees start in the sky and grow down or something. Some people think they should go sideways. Now, we'll leave that argument. If you want the tree to be upside down, you can stand on your head. The great thing about abstract trees is that they're only representing relationships between things. They're not something physical, so we can read them any way up we want. So we can read this as something that starts here and branches, or we can read it as these things that start at the top and stick together to make something. And this is one of the very powerful aspects of versatility when you're doing things with abstraction. So trees come from sticking things together. And you can imagine, we'll see how good your imagination is. One of the wonderful things about the abstract world is that you're only constrained by your imagination, not like in the world where you're constrained by things like time and money and other irritating things like that. So imagine juggling with Play-Doh, where you throw the two Play-Doh balls together so hard that they stick together. Then that path would make a tree. So trees come from sticking things together, and we can do an example like this. This is a tree coming from sticking three things together, where you stick the two things on the left together first and the one on the right afterwards. This one is the other way round, and we can ask ourselves if these things are the same. So, for example, if we add numbers up like this, we do 4 add 4, which is 8, and then we could add 2 afterwards, which is 10. Usually, because we've written things in an unfortunate straight line, we have to use these slightly annoying parentheses. Whereas really it has a two-dimensional structure like this. Now here, we're doing it the other way around. So we're going to add 4 and 2 first, which make 6. And then we'll add the 4 afterwards, which make also 10. And this time, the parentheses have to be over here when we write it in the slightly annoying straight line. And this we know, or maybe know, as the associative law for addition. We know that it doesn't matter where the parentheses go because both ways round will be the same. So these are equal if we're thinking about numbers. But the thing is that in higher math, we study things that are a lot more subtle than numbers, where there are many different layers of possibility and gray areas in between them. For example, if we do this with egg yolks and sugar, then we can mix egg yolks and sugar together, and then if we add milk and heat it up, we get custard. If we do it the other way around, we're adding sugar and milk together, and then we mix in the egg yolks, and we do not get custard. So these are not the same in the kitchen necessarily, but it depends. Because, for example, for cake, it doesn't matter so much. The usual recipe that I learnt is that you cream sugar and butter together, and then you beat in eggs, and then you fold in the flour, and that makes cake. Whereas it turns out that especially if you have an electric whisk, you can just kind of shove everything in a bowl and go, wah, and it'll be okay. Here are all the possible ways of doing it. So this one edge here shows one branch moving from left to right. And each of these arrows shows one place where one branch has moved from left to right. So I'm not changing the order of the ingredients at the top. I'm just moving here. I'm moving this branch to here, so it ends up there. From here to here, I move this big branch, takes its little baby sub-branch with it over here, and then here, the little baby sub-branch moves across to here. This branch goes first, and then this branch goes afterwards. So these are all the different ways of making cake. And I took all the cake ingredients into one of my art classes, and we did it with my students. We made it in all these different ways. So this one says, first mix the butter and the eggs. Turns out that looks really disgusting. Then you mix in the sugar, and then you beat in the flour. And if you beat hard enough, it's actually okay. It comes out all right. And this one says, start by mixing the eggs and the flour. That's also very strange. But again, if you beat hard enough, it's sort of all right. This one's really interesting, because this one you need 2 bowls. Because you have to mix the sugar and the butter first, and you have to mix the eggs and the flour separately. And then you mix the results together in a bowl. This is terrible if you're lazy like me. You don't want to wash up an extra bowl. So that one is very different. Now, we don't have ovens in art school, but I recently went and gave a talk to the Culinary Institute of America. They do have ovens. And they had an amazing lecture theatre with a kitchen at the bottom with cameras pointing down at all the... I always wanted to be on a cooking show, actually. When I was little, another thing I wanted to do was present a cooking show. So I pretended I was presenting a cooking show, and 5 pastry chef students helped make the cake in all these different ways, and then we baked it. And the thing that was interesting was that it all came out like cake. It's just that some of it rose better. So the traditional method is definitely the easiest, especially if you don't have an electric whisk. But they all come out like cake. Just, it depends. Some of them are flatter. I think this one and this one came out really quite flat. But the thing is, I like dense cake. So I don't want my cake to rise really high and be extremely fluffy. So maybe you like that more. And they were all more or less like cake. This is different from the custard situation, where if you do it the other way around, it's really not custard at all. And so in higher mathematics, sometimes, even if it's not exactly the same, it's kind of more or less the same to within some forgivable parameters. And in higher mathematics, we get to choose what counts as the same and what counts as not the same. And different things might count as the same in different situations. And this is kind of like what happens in the world as well. When we talk about equality, it's not that things actually are the same. It's really that they're allowed to play the same roles in certain situations. And this is something that usually you don't see unless you're doing a PhD in pure mathematics, probably actually in something very specific and related to category theory, which is my field. It also has a fancy name. It's the McLean pentagon. And you might wonder what happens if you want to make chocolate cake, because obviously you want to make chocolate cake. I do anyway. If you want to make chocolate cake, there's one more ingredient. And that means that each of these trees has one more branch, and there are a lot more possible ways of putting the branches together. And it turns out if you draw them all and you stick them together, then it makes this shape. So this shape has 6 pentagons on it, and each of those pentagons is an example of this with one extra leaf on it, consistently in the same place. It also has 3 squares, which have a very kind of interesting interpretation to do with doing things differently in separate bowls that don't really affect each other. And it's called an associahedron because it's about how higher level associativity happens. And this is a very key point in my field, which is higher dimensional category theory. So category theory is related to all the things that we were talking about. It looks at relationships between things and gives frameworks for studying relationships between things rather than intrinsic characteristics. The higher dimensional stuff happens because you start thinking about relationships between relationships and relationships between those. Every time you add another ingredient, you get another dimension. So somebody 3D printed this for me because in my book at some point, there's a net so you can cut it out and make this shape. So someone made a 3D print. I unfortunately lost the other one somewhere, which had a hook on it so I could hang it on my Christmas tree in the festive color of black. So if you wanted to make a cake with yet one more ingredient, you would need a 4-dimensional shape, and that would be a 4D printed object. That's a bit harder to do. We don't have very many 4D printers at the moment. So category theory, I said that mathematics is the logical study of how logical things work. Category theory is the mathematics of mathematics, which means if you unravel it, it's the logical study of how logical things work. Now, you might think that's very looped up on itself, and it sort of is, but this is what I've been teaching to art students for the last 2 years at the School of the Art Institute of Chicago. And the thing I love about it is that they are mostly students who did not do well in math before. Some of them actively hated it. Some of them didn't actively hate it, but they became art students, and so they unfortunately had to choose, because we make people choose things, and we construct somewhat artificial barriers between disciplines and boundaries between disciplines that don't really exist. Many of them hated it and were terrible at it. Many of them, interestingly, come from Asia and complain that it's the Asian math system that put them off math. Many of them say it's because math has no creativity in it, because it's all about right and wrong answers. And they're not interested in things that have right and wrong answers. They're artists. They're interested in exploration. And category theory, I think, is more about exploration and less about getting right answers. It's more about shedding light on things so that other people can solve problems, rather than solving problems directly. And my image of it is like this, that if you shine a light on something, say a flashlight, if you shine it very close, the light is bright, but you're not illuminating a very large area. If you raise the flashlight, then you will illuminate a wider area, but it will be with a slightly more diffused light. But you'll see more of an overview and a context of everything that's going on. Of course, if you raise it too high, then eventually you won't be shining any light on your object at all. So the key is to find a good distance so that you still have enough light, but you also see enough content. And that is what I think that category theory does. Now, people often ask me what is the favorite thing that I've done with food for my art students that has kind of immediately made them interested in math. And yes, it is the thing with the bagels. So we will now do the thing with the bagels. Here are some bagels. The thing with the bagels is to demonstrate what a Möbius strip is. A Möbius strip is when you take a piece of paper and when you close the ends up, instead of closing them in a cylinder, you make one twist. So that now the front is meeting the back and the back is meeting the front, and there is only one side. So this gives rise to the joke, why did the chicken cross the Möbius strip? If you draw a line all the way around it, then you get your pen on all sides of it because there is only one side. So you find that you've drawn on both sides without taking your pen off because there's only one side. This thing is very interesting topologically, but it's also kind of interesting just as a curious shape. I recently made some Möbius strip pizzas. That was quite interesting. And I fed them to my nephew, and the trouble with that, he was 4 at the time. And recently I also knitted a Möbius strip, which was very exciting, and I showed it to my nephew, and he said, I want a real Möbius strip. And I said, what do you mean? What do you mean by real? He said, the kind you can eat. So someone said to me, yes, I made a rod for my own back. Anyway, another thing that you can do to demonstrate that a Möbius strip has only one side is that you can cut a bagel open along a Möbius strip. So instead, usually we cut bagels open like that, and that's kind of slightly dull. But if you twist your knife as you go, then you can cut it open along a Möbius strip. And this is what happens. I'm going to make my knife go in here. No, my knife go in here, and then I'm twisting. Now the knife is kind of horizontal, and then I'm going to keep twisting so that the knife will get back to the vertical. And then all I have to do is try to meet the other cut without cutting off my fingers in the process. I quite like having 10 fingers. Useful for playing the piano. So now, we see that it doesn't come apart, but it does open in halves, where if you look at it locally in each position, it looks like it's cut in half, but globally, it is not cut in half because the cutting surface only has one side. So you could take some cream cheese, and you could spread cream cheese all over the one side without ever taking your knife off. The other thing you could do is you could get a Möbius strip of smoked salmon, and you could put that on the inside. Now, when I first made a video on this, because people online are very interesting, lots of people said to me, that's the stupidest thing I've ever seen. Someone said, how are you going to toast that? Well, I don't like toasting anything, but fine. Then someone said, you're solving a problem that didn't exist. And I was like, well, I'm not saying this is the best way to eat your bagel. I'm just saying it's an interesting mathematical demonstration. But do you know what? The last time I made this bagel, it was the one that went viral. So there's a side story to that, which is that when I first started making YouTube videos, and it was on category theory for grad students, and we got really excited when we hit 10,000 views and we opened a bottle of bubbly. And one of my colleagues said to me, yeah, well, you know, you'll never get 1 million views without taking your clothes off. Well, my last bagel video has 8 million views. Also, after I made that video, the bagel that they brought me for that video was the most delicious bagel I have ever tasted. So I didn't want to waste it, so I asked if I could take it home with me. I didn't have anything to carry it in, so I just kind of vaguely wrapped it in a napkin and shoved it in my bag. And a few hours later, I thought, I'm really hungry now, so I got it out of my bag, and I realized the brilliance of the Möbius bagel, which is that it will not come apart in your bag. So you will not get cream cheese everywhere. So this is now my favorite example of a mathematical discovery that was just there for sheer curiosity. And then an application happened later. And this happens with many things. Number theory that was developed 300 years ago is now at the center of internet cryptography. And they didn't have any idea that the internet would exist. They didn't have any idea that computers would exist. The Platonic solids are from 2,000 years ago. The icosahedron had no known naturally occurring form and no use until the 1950s, when microscopes were developed that were powerful enough to look at viruses. And it was discovered that viruses are many of them are icosahedron shaped. So that was a 2,000-year delay between the discovery of the icosahedron and some use for it. And that's yet another reason why I think we shouldn't just focus on usefulness, but we should allow people to do things that are fascinating. The human capacity for curiosity, I think, is amazing. And if we do things logically, then what we're doing is we're gradually putting more and more things into the realm of logical understanding. Now, I don't claim that we can understand everything in the world using logic, and I don't think that we ever will. Some people may disagree. But every time you answer a math question, it causes more math questions. But there's no way you can ever answer them all, because every time you answer one, you make more of them at the same time. But I think what we should do is be trying to put as much stuff into the logical core of what we understand as possible. I think logical thinking is like the core muscles, where there's no activity where you only use core muscles. But if you have a strong physical core, that enables you to engage the rest of your muscles better. And I think if we have a strong logical core to how we think, that enables us to engage the rest of our brain power better. And for me, the most beautiful stuff is right at the interface of the things we can explain logically and the things we can't, just beyond that. So I can analyze a piece of Bach about why it makes me cry because of the chord progressions and the suspensions or whatever. But beyond that point, why does that suspension make me cry? That is where it's beautiful, the bit I just can't quite explain. And so I have an image of the logical core being this sphere at the center of our understanding. And the more we put inside it, it grows. And as it grows, the surface of it grows. And that means that we have more and more access to the beauty that's on that interface. And that's why I think that we should all study mathematics. Thank you very much.
That was terrific. Thank you. All right. Oh, and I closed the online questions. But as the line forms here, let me go to the online question. The first one, you have a lot of talents: cooking, juggling, piano. What talent do you hope to learn next, and how will it help you demonstrate math?
That's a lovely question. I thank you, person online, for that. I have been trying to perfect how to make French macarons for a really long time. And I started doing this because I think they're really delicious. And because I once spent a wonderful research month in Paris, and I was very worried that I would get really fat. I used to be really fat, and I lost all that weight, and I don't want to put it back on again. But when I'm around a French patisserie, it's a bit of a disaster. And so I decided that I would only eat macarons, and that I would go across Paris trying all the macarons in Paris, making tasting notes. And because macarons are very small, and they're actually not that full of calories, and they're so delicious that I'm satisfied by just a small amount of it. And then I moved to Chicago, where I wasn't able to find macarons that really lived up to it. So I decided, well, I'll just try and make them myself. Very difficult. And so sometimes I can do it, and sometimes I can't. And it's really bugging me because I feel like I've reduced it very, very scientifically. I've controlled all the aspects of it, and still sometimes something strange happens. So I would love to pair up with a chemist or a physicist to understand the chemistry and physics behind macarons, so I can really understand. I've read every macaron troubleshooting guide on the internet, all of them, every single one. And there still seems to be something I can't understand. Maybe that's what makes them so beautiful.
Terrific. Let's go in the theater here.
Sorry, this is less of a question and maybe a bit of an advertisement. There is a conference coming at the University of Waterloo called Bridge Conference, which is specifically aimed at the intersection of mathematics, art, and the humanities. And I could recommend that to everybody.
Oh, yes, I think I've heard about that. I think I know some people who are going. Sounds wonderful.
Thank you. Let's have the next question in the theater.
It's William smart juggler, is it?
Yes.
Yes.
This is a rather obscure question, but I have to ask. Have you ever tried making custard backwards? And if so, what was the result?
Do you mean with the other tree?
Yes.
It just doesn't do anything. Because what happens when you whisk the egg yolks with the sugar is that a chemical reaction happens. And that you can see it happen because it completely changes consistency. It's not just that they get mixed, they actually physically change. Eggs are amazing. Let's just take a moment to thank chickens. One of the things I love about what eggs do is that you start with something that looks like an egg, and you end up with something that doesn't look like an egg at all. Because when you make cake, you take eggs, flour, butter, and sugar. None of those looks like cake. And then you make cake. That's why it's exciting to me. That magic is like pure math, where you take some very basic things and then you make something incredible out of it. So yes, if you do it backwards, it doesn't do that chemical reaction, and it's more like just kind of wateriness.
All right. Thank you.
All right, I'll go to an online question. Have you ever felt math-phobic yourself?
Have I ever felt math-phobic myself? There have been some times, and this is one of the reasons that I have sympathy for it. In certain types of math class, which are all about having some funny trick up your sleeve, and that to be good at it, you just have to have a huge bag of tricks that you know which trick to throw at it. There are lots of different types of math. It's not all just one thing. Some are more about using tricks to solve problems, and some are more about examining the deep structure that's inside mathematics. And this kind is the kind that I really like. I was always a bit baffled by the other kind because it just seemed like I needed to, it's like a situation where you just have to be really rich or something, where you need a whole load of tricks and then you throw it at it and then it's like doing a magic trick and no one really knows what you've done because you've done this magic trick, which looks very fancy, but I prefer the kind where someone explains every step of the way and where all the proofs actually illuminate what's going on rather than the kind where the proof goes, done.
Thank you. In the theater.
I'm just wondering, what made you decide to show ordinary things into mathematics?
What made me to decide to?
What I meant is, for example, bread or let's say hair or whatever, you decide to get into mathematics to show this.
Oh, that's a lovely question. Now, the trouble with abstract mathematics is it's abstract. And that's the good thing about it, but it means it's difficult to show what's going on without having something that everybody can relate to. And if you relate to something and feel something about it, then you're more likely to have a lasting impression of it. Whereas if you don't feel anything, then it will just come and go. And so when I teach, I always tell stories based on my life and my experiences. This comes a lot from my piano teacher, who was a wonderful teacher, and she taught me all the principles of education. She instilled in me a belief that education is the most important thing I can do. And she always told hilarious stories when she was teaching piano. And so she talked about dog training and ironing and all sorts of things. And so I also do that. And I discovered that the stories I tell that involve food made the students wake up. Not to say they were asleep, but they woke up particularly. But it's also because I genuinely do think that math is everywhere, and not just in splitting restaurant bills and things. I see math inside everything that we do. And so to make good on that fact, I can show what math I see in everything. And so I try to use as diverse a range of things as possible so that things can appeal to different people. And also so that it's not like, now we're doing math. Oh, now we're not doing math, where you turn your math brain off. So now maybe if you see someone with a braid in their hair, you'll think about math where you didn't before. Or when you eat cake, you'll find yourself thinking about math. And so I do this with my students so that I talk about riding the train or something, so that maybe when they're riding the train, they'll be reminded of math rather than turning off their math brain when they leave the classroom. Thank you. Thank you.
Thank you. In the theater.
Thank you for your lovely talk. Anyway, I was just thinking, you did your PhD in math, so you must be dreaming math, thinking math. And you demonstrated to us how you could take relationships and permutations of relationships and construct a three-dimensional object from that. Mm-hmm. And I wondered if when you were doing your PhD or after, if you've ever seen a solid object like an icosahedron and thought, how many different relationships does that represent and what is the entanglement? And if you've ever had any interesting insights like that.
I often look at three-dimensional structures and see the relationships between the things inside it and also see the relationships with other things. And I have the kind of brain, I was just talking to my students about it this week, I have the kind of brain that loves seeing relationships and commonalities between things. And that is the aspect of mathematics that appeals to me the most. And category theory, some people say it's the theory of analogy, where you're always finding analogies between things. And then you can learn, of course, nothing is exactly the same, but you can learn from the parts that are similar. And I think this makes math into a very unifying subject. And in general, in life, I also prefer finding commonality with people and finding things we have in common, rather than finding differences all the time. And I think a lot of the world at the moment is caught up with finding differences instead of finding commonalities. So I do, yes.
But is there any sort of biological equivalent? I was thinking about, the Fibonacci sequence and how that makes spirals and stuff. Is there anything that you've seen that you thought, wow, that's really unique, like your viral thing?
Well, there's a lot of it in music that I often see the structures there. And when I look at buildings, as soon as I looked at the outside of this amazing building here, I started seeing math all over it in there. And sometimes when I teach platonic solids to my students, I just get them to build them without telling them what they're supposed to look like, just saying they're supposed to be symmetrical all the way around. So they start sticking triangles together, and sometimes they follow their nose, and it doesn't make a platonic solid, but it makes something else that's very interesting. And so I often see those structures. I was giving a talk at the Sage Gateshead for the BBC Free Thinking Festival a couple of weeks ago, and the outside of it looked exactly like a manifold to me. And if there are mathematicians in the audience, you know that that's like a kind of a surface, but it has to have a system of charts on it that tell you how you could map it to a two-dimensional map if you were going to. And this thing had this grid structure on it, and I just immediately looked and I thought, oh, that's like a manifold with a chart on it. So I do see those things all the time.
Aiden, how about the last question?
So how there is pure maths, why do you think there isn't really pure science?
That's an interesting question. I think there is pure science. I think that it often isn't called pure. So even in physics, for example, there is theoretical physics and there's also applied physics. So there's also theoretical science and experimental science, where the theoretical science is where scientists sort of make theories in their head from basic principles. And experimental science is where scientists do experiments and try and draw conclusions from those experiments. And ultimately, we want the two things to match, so that the things that we make up in our heads actually match the experiments that we do in the world.
But more of just doing science for the sake of science. I find that I was in the science fair recently, and they wanted my project to have a use.
Yes.
And it didn't really.
Isn't that frustrating? So did you find that frustrating?
What?
Did you find it frustrating that they wanted it to have a use?
More annoyed.
Oh, yeah, even worse. And so I think this is a great lesson that we can all learn from you. That yes, it is kind of annoying if things have to have a use all the time. And unfortunately, or maybe fortunately, but unfortunately, I think it is something that a lot of people have decided we should focus on to make science interesting to young people, to show that it's somehow relevant to their daily life. And I think that might help some people. But in the process, we're missing helping some other people who are so fascinated by it for its own sake and for the structures that you see inside it. And we should be careful not to neglect those people, because they might make the greatest theoretical scientists of the future. Thank you.
Ladies and gentlemen, thank you. That was wonderful. That's so good. That's so good. Yeah, now we're doing that.